All right, welcome to the deep dive. Today we're diving into something that I think is absolutely fascinating, meteor airbursts. These are those events where we're not talking about those tiny little shooting stars that burn up harmlessly high in the atmosphere, but those larger space rocks that come screaming in and explode dramatically.
And these are no pebbles we're talking about here. These are things ranging in size from, a small car to even a house. And when they slam into the atmosphere, they create those incredible fireballs that sometimes we call bolides, right?
Yeah.
And when they get really, really bright, they earn that title of superblide.
Yeah, it really captures that sort of that awe-inspiring nature. And I think, when most people think about kind of a benchmark event, the one that always comes to mind is the 1908 Tunguska event in Siberia. I mean, that really put this phenomenon on the map, so to speak.
It did. That was a huge one. Estimates place that impactor at something like, 50 to 60 meters across. So, think like a small apartment building, and it detonated, several kilometers above the ground. And what's crazy is the shock wave flattened a forest over 2,000 square kilometers.
That's huge. I mean, that's like, a major metropolitan area just wiped out.
Right. And here's the thing, only an estimated 3 deaths, and it's really just because it happened in such a remote location.
I guess that's a silver lining in a way, right?
Yeah.
But it also it emphasizes just how powerful these things can be.
Absolutely. It's almost like nature gave us this experiment, to see what can happen. If something like that hit a populated area today, I mean, the consequences are just unthinkable.
Yeah, and what's really changed since Tunguska is our ability to detect these things. Back then, it caught everyone by surprise, but now we have all sorts of technology listening and watching.
Right, like those infrasound sensors. They're originally designed to detect nuclear tests, but they pick up these air bursts too. And then you have satellites with infrared. They're constantly looking down at the Earth.
So we're not in the dark anymore, so to speak. We're actually getting a much clearer picture of, how often these things are happening, where they're happening, what kind of energy they're releasing.
And that data is crucial because it allows us to study these events like never before. We can look at the frequency, the size of the objects, the energy involved. It's really remarkable.
And that's really what we want to unpack today. We're going to, delve into the science behind these atmospheric explosions, look at some historical examples, some recent ones, really try to, give you a deeper understanding of what's going on when these space rocks slam into our atmosphere.
Yeah, because it is a violent process.
Yeah.
I mean, you've got these objects entering the atmosphere at speeds of at least 11 kilometers per second.
Wow, that is fast.
And as they hit that denser air, they encounter something called ram pressure.
Ram pressure. Okay, that sounds intense. Can you explain that a little bit? Like what is ram pressure?
Imagine this. You're driving down the highway at, a good speed, and you stick your hand out the window.
Okay.
You feel that force of the air pushing against your hand.
Right, yeah.
Now, multiply that by, thousands of times, and that's basically ram pressure. It's the force of the air being compressed incredibly rapidly in front of this speeding object.
Oh, wow. So it's not just friction like the air rubbing against the object, it's actually this pressure wave building up.
Exactly. And this compression, this rapid compression, causes the temperature to spike dramatically.
Hmm.
Think about, pumping up a bicycle tire and how the pump gets hot. It's kind of similar.
Ah, okay. So it's that energy being converted into heat. That makes sense.
Yeah, and that's a big reason why most meteors don't actually make it to the ground. They either burn up completely or they break apart due to this pressure.
That makes sense. I always kind of wondered why we don't see more, meteorites on the ground given how many of these things are happening.
Right. Well, it's this intense pressure and heat that's doing most of the work. But that brings us to that term explosion, right? When we talk about air bursts, we use that word, but it's not like a traditional explosion.
Yeah, I was just going to ask about that because, we often see the energy of air bursts measured in kilotons or megatons of TNT, which makes them sound like bombs.
Right, but it's a different kind of explosion. These objects don't have any explosives in them, and there's no nuclear reaction happening. It's purely the result of this incredible ram pressure reaching a critical point.
So how does that actually cause the meteor to explode?
Well, as it's plunging through the atmosphere, that pressure keeps building up.
Hmm.
And at some point, the force of that pressure just overwhelms the structural strength of the object.
So it just can't hold itself together anymore?
Exactly. It's like, imagine you drop a glass vase on a concrete floor. That sudden stop, that transfer of energy, it shatters the vase. Well, the atmosphere is kind of like that concrete floor for a meteor. It's this incredibly strong barrier that it's slamming into.
And all that energy from its motion just gets released all at once.
Right, and that's what causes that bright flash, that shock wave. It's all that kinetic energy suddenly being converted into heat and light and sound.
I see. So it's not really a chemical explosion, it's more of a physical one.
Yeah, and our sources mention something else that's really interesting, this superheated air.
Okay, what about that?
Well, as the meteoroid is heating up and the
Mhm.
pressure is building, you get these tiny cracks forming on the surface.
Okay, yeah.
And that superheated air, which is basically plasma at this point, it gets forced into those cracks.
So it's like getting under its skin almost.
Yeah, and once it's inside, it exerts this tremendous pressure from within. It's kind of like, blowing air into a balloon. It just inflates it, it stretches it out.
Ah, so it's like the object is being attacked from both sides now.
Exactly. And that just accelerates the whole disintegration process. It starts to break apart from the inside out, which is why it looks so much like a detonation.
Wow, so it's like this perfect storm of pressure and heat just ripping it apart. And this is happening all the time, right? I mean, how often do these airbursts occur?
Well, we have programs like the Earth Impact Effects Program, or EIEP, that use models and observations to estimate that.
And it's actually surprisingly frequent, right? Even for some of the larger ones.
It is, for example, an object about 4 meters across that could produce an airburst with an energy of about, 0.75 kilotons of TNT. That's like a small conventional bomb.
Yeah.
Those are estimated to happen about once every 1.3 years on average.
Wow. So more often than I would have thought.
Right, and if you go up to, say, a 10-meter object, that can create a 19-kiloton airburst, and those are estimated to happen about once every 10 years.
Okay, so the bigger they are, the less frequent.
Exactly, and when you get up to the Tunguska size, 50 meters across, those are much rarer. Estimates put them at about once every 764 years.
Wow. So Tunguska was really a once in a millennium kind of event.
Yeah, pretty much. But even those smaller ones, they're still happening pretty regularly. And we have that world map from 1994 to 2013. It shows all these bolide events that were detected.
Yeah, it's amazing to see how widespread they are. They're not just happening in one particular part of the world. They're literally happening all over the globe.
Exactly. And it really highlights that, Earth is constantly being bombarded by this cosmic debris.
Yeah. Now I want to shift gears a little bit and talk about some specific events. We've mentioned Tunguska, but there are some really intriguing historical accounts from before the 20th century. One that stands out is the Xinjiang event in China in 1490. Although, the reported death toll of 10,000 people, that's probably a bit of an exaggeration.
Yeah, modern researchers are pretty skeptical of that number.
Mhm.
But even if it's inflated, the fact that there's a record of such a devastating event, it suggests that something really significant happened.
And it makes you wonder, could it have been another Tunguska-like event that just happened to occur over a populated area?
It's definitely possible.
Mhm.
And then there's the 1626 Wangongchang explosion in Beijing. That one's really interesting because it happened at a gunpowder factory.
Oh, wow.
Yeah, so the official explanation at the time was mishandled gunpowder, which, makes sense. But there's this speculation that it might have actually been an airburst right over the factory.
Oh, that would explain the massive death toll, right?
Sure.
20,000 people reportedly died in that explosion.
Exactly. And it really highlights how difficult it can be to know for sure what happened in these historical events,
Mhm.
without the scientific tools that we have today.
And then there's that 1888 report from Slimanaya in Iraq, where a study claimed a meteorite might have actually killed one person and paralyzed another.
That's a really intriguing case. Although there's still debate about whether a meteorite was actually responsible. It just goes to show how little we know about some of these past events.
Yeah, and it makes you appreciate how much our understanding has advanced since then.
Hmm.
Now, moving into the 20th century, we have the 1919 Michigan event. That one sounds pretty dramatic. A gigantic meteor, a bright flash, people reported thunder, even earthquake-like shaking.
Yeah, and it lasted for 3 minutes, which is a long time.
It really shows that even, those smaller airbursts can have a big impact on the ground.
Absolutely. It's not just a light show. There's real energy being released into the atmosphere that can shake things up.
Then you have the 1930 Curaçao River event in Brazil, sometimes called the Brazilian Tunguska.
Yeah, that one's a bit of a mystery. There's this possible impact crater in the area, but it could be from a much older event.
And the energy estimates are pretty high, around 100 kilotons of TNT.
Right, so something definitely happened there, whether it was a recent airburst or an older impact.
Yeah, it's just hard to say for sure without more evidence. The 1932 Arroyo Molinos de Leon event in Spain, that one's interesting because it might be linked to the December Delta Arietids meteor shower.
Yeah, which suggests that some of these larger objects come from, known streams of space debris.
So it's like we can trace their origins in a way.
Exactly, and that can help us understand their composition, their orbits, all sorts of things.
Now, the 1935 Guyana event, that one's kind of confusing. There are reports of a huge meteor fall that devastated a forest, but some people think it might have been an airburst.
Yeah, it's tough to say for sure based on the reports we have. The damage patterns suggest an airburst, but, it was a long time ago.
And then you have the 1947 Sekota-Alin meteor in Russia, which was just massive. It produced an incredible fireball and resulted in the largest meteorite fall in recent history.
Yeah, over 23 tons of fragments were recovered.
That's a lot of space rock.
It is. And even though it did produce meteorites, the initial entry would have involved, significant airburst phenomena. That's what created that huge fireball and the sound that people heard for hundreds of kilometers.
And then there's the 1963 Prince Edward Islands bolide. That one's really interesting because it was picked up by infrasound sensors.
Yeah, but there's some debate about whether it was actually a meteor or a secret nuclear test.
Oh, wow.
Yeah, it was the Cold War, and there was a lot of secrecy around those things. So it's
What?
possible that this event was misidentified.
That's a pretty big mix-up.
It is, and it shows how important it is to have multiple sources of data to confirm these events.
Definitely. Now moving on to some smaller events. The 1966 Kincardine fireball in Ontario, Canada, that one was pretty impressive visually, even though the energy release was relatively low.
Yeah, it just goes to show that even those smaller airbursts can create quite a spectacle.
And then you have the 1969 Alen Divide in Mexico and the 1976 Jilin Bolide in China, both huge fireballs that resulted in some of the largest meteorite falls of the 20th century.
Right, and those events really highlight that even those objects that reach the ground, they still go through this intense interaction with the atmosphere.
Yeah, it's not like they just gently float down.
Right, they're being heated, they're breaking apart, they're creating these shock waves.
And then there's the 1993 Lugo superbolide in Italy, which was caused by a really fast-moving, low-density meteoroid.
Yeah, that one's interesting because it shows that not all meteoroids are created equal. That their composition and their speed can really affect how they behave in the atmosphere.
Yeah, it's not a one-size-fits-all kind of thing.
Definitely not.
Now, in the 21st century, we've had some even more well-documented events, like 2008 TC3. That was the first asteroid ever detected before it impacted Earth.
Yeah, and they actually found fragments of it in Sudan. That was a huge step forward for planetary defense.
Yeah, it shows that we're getting better at tracking these things and predicting where they're going to hit.
And then there's the 2012 Sutter's Mill meteorite in California, Nevada. That one was pretty small, but it still produced some nice meteorite samples.
And then, of course, there's Chelyabinsk in 2013, the biggest airburst since Tunguska.
That one really captured the world's attention, and for good reason. The shockwave caused a lot of damage and injuries.
Yeah, it was a real wake-up call about the potential dangers of these things.
Absolutely. And then, we have that 2014 event over Papua New Guinea, which was potentially an interstellar meteor.
Yeah, that one's just mind-blowing, the idea that this little piece of rock came from outside our solar system.
And it was moving incredibly fast. I mean, faster than Oumuamua, which was that other interstellar object that made headlines a few years ago.
And then finally, we have the 2018 Kamchatka superbolide. That one was the biggest since Chelyabinsk.
And it happened over the Bering Sea, so not a lot of people were aware of it at the time.
But it just goes to show that these events are still happening, and they can be quite powerful.
Yeah, and it highlights the importance of having, global monitoring systems in place. We need to be able to detect these things no matter where they happen.
Now, looking at the JPL data, it's amazing to see how many of these smaller airbursts are happening every year. Dozens of them.
Yeah, it's like a constant rain of space rocks, although most of them are, too small to do any real damage.
But it's still important to track them to understand, the overall population of these objects.
Absolutely. And it all helps us refine our models and get a better understanding of the risks.
So I think it's clear that meteor airbursts are not just some, theoretical threat. They're a real phenomenon that's happening all the time.
And they can range from these these tiny little events that nobody even notices to those massive explosions that can cause significant damage.
Yeah, and what's really amazing to me is that the explosion itself is not like a conventional bomb. It's this incredible conversion of energy.
Right. It's all that kinetic energy from the object's motion suddenly being released as it slams into the atmosphere.
It's a pretty powerful reminder of the forces that are at play in our universe.
Definitely.
So, as we wrap up today, I want to leave you with a thought. Given how much our ability to detect these events has improved, what are we doing to prepare for those really big ones, the ones that could have a truly devastating impact?
It's a question that a lot of scientists and engineers are working on right now. And it involves things like, better detection systems, maybe even developing ways to deflect those objects.
Yeah, it's like planetary defense is becoming a real thing.
It is.
Yeah.
And it's something that we need to take seriously.
Well, that's a pretty thought-provoking note to end on. Thanks for taking this deep dive with us today. It's been fascinating.
My pleasure. It's always great to talk about this stuff.
Yeah, it's amazing to think about, all these things that are happening above our heads all the time.
Definitely. Makes you feel small, doesn't it?
It does, in a good way, though.
Yeah, I think so.
Well, thanks again for joining us, and we'll see you next time on The Deep Dive.
See you then.